Hi, I'm going to be talking about my work with Mike Sachs on randomized reductions to the random strings. So to motivate the topic of this talk, let me introduce the minimum circuit size problem, MCSP. This is a fundamental problem in complexity theory, on which there's been a lot of work recently. In the problem, you have as input a Boolean function f on n bits given by its truth table of size capital N, 2 to little n, and a size parameter s. And you want to say yes, the function has circuits of size at most s. So this problem has relevance to many different areas of theoretical computer science: circuit complexity, learning theory, cryptography, proof complexity, and so on and so forth. And it also captures important practical problems of circuit minimization. So the minimum circuit size problem is an example of a so-called meta complexity problem, a problem, a computational problem that is about complexity and whose complexity we want to know about. So meta complexity problems are meta complexity studies the complexity problems that are themselves about complexity. And there are other problems of this nature. So for example, the classical problem of computing the congruent complexity of a string, k of x, that's defined given a universal machine U that's fixed. K of x is the minimum size of a program such that U produces x on that program with an empty input. In some sense, k of x measures how much x can be compressed, with the decompressor having unlimited computational resources. So a promised version of this problem, k of c comma s, where c and s are functions of the size of the input length, is a problem where you say yes if the congruent complexity is at most s of size of x, and no if the congruent complexity is greater than c of size of x. So if you want to study compression where the decompressor has polynomial time resources, limited resources, then you can define a time-bound version of congruent complexity, k superscript t of x. And again, the universal machine U is fixed, and k superscript t of x is the minimum size of a program, such that U outputs x on program P and empty input within at most t of size of x steps. So t is some fixed polynomial, say n squared. The promised version is defined analogously to before. So the question is, how hard are these problems in terms of their complexity? It's easy to see that the minimum circuit size problem is an NP because you give an entire truth table, and if you want to know there's a circuit of a certain size for the function computed, the function corresponding to the truth table, you can just guess the circuit C and verify that C computes F correctly. And the way you do that is for each x corresponding to an entry in the truth table, you compute C of x and checks that C of x equals that entry. This is polynomial time because verifying any given input takes time close to s. The capital N inputs takes time proportional to s times n. And for similar reasons, k superscript t is an NP for any polynomial time-bound t because you can guess a program, run for t steps, t is a polynomial, and check that it outputs x. And also check that the program is of size at most s. So classical result in computer theory shows that k, the congruent complexity, is uncomputable. And here's a quick proof sketch for that. Under the assumption that congruent complexity is computable, there's some procedure, say A, that computes it. Then we can think about the task of finding the first string of length n for which A says that it has congruent complexity at least n. So by counting arguments, we know that such a string exists. So which is the first string of length n, such that a first string y of length n, such that y with parameter n is rejected by A. Just by assimilating A like cryptographically an E string in order, you can determine this. But in order to find such a y, it only requires the representation of n, which is log n bits long, together the program for doing what I just said. So it's log n plus order 1 bits. But that's a contradiction because you're describing a string y of congruent complexity greater than or equal to n using log n plus order 1 bits. When n is large, this is impossible. So there's various kinds of evidence that MCSP is not in polynomial time, particularly under cryptographic assumptions. If one-way functions exist, which is a standard cryptographic assumption, then MCSP is not in P. And this is shown using the celebrated natural proofs framework of Ross, Pro, and Rubich. because the polynomial time algorithm for MCSP implies that natural proofs useful against exponential size circuits, sub-exponential size circuits exist. That can be used to break exponentially secure one-wave functions. So this is a well-known result. And it's a very similar way, if one-wave functions exist, then K superscript T is not in P for polynomially bounded T. A major open problem in complexity theory is whether these problems are NP complete. So they're both on NP, there's evidence that they're hard, are they NP complete? As for the Kolmogorov complexity, of course, it's uncomputable. We can ask for which classes are reduced to Kolmogorov complexity. So for which classes is it hard, in the sense that every problem in the class reduces to it using a certain resource-bounded reductions. And this question has been studied extensively by Eric Allender and others. Various conjectures have been made. We still don't understand the situation properly. So in general, the question of NP completeness is, of course, a fundamental question. The vast majority of natural computational problems in NP are either known to be in P or they're known to be NP complete. There are some exceptions, for example, problems that are used to base cryptography on, such as factoring, discrete logs, and lattice problems. These are in NP, but they're not believed to be in P, but they're also not believed to be NP complete. And then there's graph isomorphism, which is actually in quasi-polynomial time, so it's very unlikely to be NP complete. And then these meta-complexity problems, MCSP, K superscript T, and various variants of them. And here we have no evidence that they're not NP complete, and we have evidence that they're not in P. So Levin is supposed to have delayed publishing his NP completeness result because he wanted to show that problem similar to MCSP was NP complete. This is already in the early 70s. It's more than 50 years later, and we still don't know. And these two problems have some main examples of computation problems that are believed by many to be NP complete, but aren't known to be. And that's what we want to study. Are these problems NP complete or not? If they are, why does it seem to be so hard to show that they're NP complete? So the difficulty of showing NP-Hardnes. Why is it so hard to find a reduction from SAT to MCSP and K superscript T? This is something that people have tried to do for a long time and haven't succeeded. Intuitively, the reason why it's so hard is because instances of MCSP or K superscript T are random-like. MCSP is really about distinguishing functions of high circuit complexity, which behave like random functions, from functions of small circuit complexity, which are more structured. And similarly with K superscript T, I mean, K superscript T is about distinguishing random strings that are incompressible from strings that are compressible. So in fact, the natural proofs framework is a way of making this explicit. So that's an intuitive reason, but can we say something formal about the difficulty of showing NP-Hardnes? And this is something that this paper of Cabinets and Tsai that I mentioned earlier talks about. They consider the question of NP-Hardnes of the circuit size problem under certain restricted kinds of many one reductions. So in particular, they consider unnatural polytime reductions to MCSP. A natural reduction is a reduction where the size of the output and the parameter depend only on the size of the input. So the reduction has some input x, and then f of x, there's some kind of like y that it maps to and some parameter s. And both the length of y and s depend only on the length of x. And this is the case with standard NP-Hardnes reductions. So for example, if you're reducing to clique, you want a graph and a parameter. The size of the graph depends only on the size of the input. The size of the parameter depends on the size of the input as well. And this is the case for all natural optimization problems. So all the standard NP-Hard problems are hard on natural reductions. But what Cabinets and Tsai showed is that if MCSP is NP-hard on natural reductions, then E does not have polynomial size circuits. The exponential time does not have polynomial size circuits. And this is something that we don't know, and that seems quite hard to prove. It's something that we believe. So this theorem doesn't say anything about whether MCSP is likely to be NP-hard or not. It just says something about whether we're going to be able to prove that in the near future and given current techniques. So their results suggest that NP-Hardnes of MCSP under natural reduction is likely to be hard to show. And here's a proof sketch how the result works. So let's say there's a production F, which maps which reduces SAT to MCSP. So yes instances of SAT get reduced to yes instances of MCSP. No instances of SAT get reduced to no instances of MCSP. And the idea is fairly simple. It's that you can generate no instances of MCSP efficiently by efficiently generating no instances of SAT and then running the reduction on them. And it seems hard to generate no instance of MCSP, especially when the parameter is large, because that corresponds to hard Boolean functions. And generating the truth table of a hard Boolean function in polynomial time corresponds to superpolynomial low bounds for exponential time. And that's believed to be hard. So as long as the reduction is going to give you something with a large parameter, an MCSP instance with a large parameter, just by using this argument, we'll get that exponential time doesn't have polynomial size circuits from it. But of course, there's possibility that the parameter is small, that it's, say, polylog n. But in this case, we can use an alternative argument where we can show that in this case, all of NP is in quasi-polynomial time, and we can show that in that case, exponential time also requires polynomial size circuits. So in either case, depending whether the parameter is small or large, we get circuit low bounds, which we don't yet know how to show, and which seem very hard to show. And exactly the same argument is also going to get you strings with high k superscript t complexity. And k superscript t complexity, if the k superscript t complexity of a string is high, say for t equals n squared, that also means the circuit complexity is high. So it's a stronger conclusion. So there's been various follow-up works, kind of relaxing the notion of reduction or considering stronger kinds of reductions. For example, Murray and Williams show unconditionally that MCSP is not NP-hard under D-log time projections, which are a more restricted kind of reduction, but already enough to show NP-hardness for most natural problems. If you remove the naturalness restriction on M reductions, then the NP-hardness of MCSP implies that X doesn't equal CPP, which is also a long-standing open problem. Hitchcock and Pavan consider NP-hardness under truth table non-adaptive reductions, and show that in that case also X does not equal CPP. And in a joint work with Mike Sachs, we showed that the MCSP is NP-hard under natural adaptive reductions, then exponential time does not have polynomial size circuits. Yeah, please ignore the A's here. I was clearly tired or drunk when I was making this slide. So the question is, what about randomized reductions? Randomized reductions are used quite often in complexity theory. What about randomized reductions? Possibly using randomized reductions to show NP-hardness or MCSP. So cabinet-psi type obstructions don't hold anymore for randomized reductions, because cabinet-psi obstruction is about deterministically generating some object that we don't know how to generate deterministically, namely hard Boolean function, but we do know how to generate randomly. Just by a uniformly random string is going to have high circuit complexity. So randomized reduction could generate a uniformly random string, which is close to maximum circuit complexity, maximum KT complexity, and so cabinet-psi obstacle doesn't apply anymore. And it's also the case that randomized reductions have been shown to be useful for other metacomplexity problems. For example, there's a space-bounded notion of Kolmogorov complexity, which is known to be hard for P space. This should be P space, not X, under randomized adaptive polytime reductions. And Kolmogorov complexity is known to be hard for any XP, for all of non-touching exponential time, under randomized non-adaptive polytime reductions. This is a recent and very interesting result of Hirahara. So what are our results? So what we wanted to show was that even randomized reductions showing MCSP is NP-hard would have sort of unlikely or hard to prove consequences. We weren't quite able to do that. Instead, we showed some results for Kolmogorov complexity and K superscript T complexity, hopefully interesting in their own right. So our first theorem is, if there is a randomized polytime non-adaptive reduction, which also needs to satisfy a natural condition called polynomial honesty, which I won't get into here, from a language L to K of C of n minus omega log n for some polynomial time computable C, then this language L is an AM and co-AM. So why is this interesting? Well, suppose we want NP-hardness of this promise problem, then let's say L is SAT. That would imply that SAT is an AM and co-AM, but SAT and AM and co-AM is known to imply the polynomial hierarchy collapses, which is something we don't believe. So what that means is it's unlikely that there exists a polynomially honest randomized polytime non-adaptive reduction from SAT to K of n minus omega log n, for example. So this is actually giving us more information in a certain sense than cabinet-psi obstruction, because cabinet-psi obstruction just says that certain kinds of reductions are going to be hard to establish, while this result says that certain kinds of reductions are unlikely to hold because they lead to unlikely consequence, namely the polynomial hierarchy collapsing. And interestingly, we get a sort of like dichotomy result in the sense that when the gap between yes and no instances omega log n, there's a reduction from L to the promise problem, then L is an AM and it's a co-AM. While if the gap is order log n, then in fact all of nx reduces to this promise problem. So this order log n seems to be some sort of threshold parameter where exceeding it makes reductions makes it much harder to reduce a language to the promise problem. And second result is about K subscript T complexities. Suppose there's some time-bound T prime that you fix for your reduction. So you say, let's say, n to the 10th. Then there's some time-bound T, let's say n to the 20th, such that K subscript n to the 20th of n minus omega log n is not going to be hard for SAT under n to the 10 time reductions, non-adaptive reductions, unless one of these two unlikely things happens. Either E has non-atomistic circuits of size 2 little n, or N equals co-Ne, both of which are statements that many complexity theorists disbelieve. And this sort of assumption that this T prime, some polynomial bound function, it's sort of natural too, because for all known NP-completeness result, for a language, the reduction runs in some small fixed polynomial time-bound T prime. So you might think, is it a bit artificial that we are restricting this time-bound T prime and then choosing T as a function of it rather than the other way around? The fact is that for almost all NP-complete problems, in fact, all the ones that I'm aware of, T prime is indeed some small fixed function. So this doesn't rule out the possibility that, let's say if you want to show that K superscript n to the 20th of n minus omega log n is NP-hard, that you could do it using randomized non-adaptive reductions that run n to the 40 time. But it does say it's unlikely if you only have reductions run n to the 10th time. So let me quickly mention some proof ideas for these results. So first, for proof ideas for theorem 1, the theorem about reductions from L to approximating common complexity. We first show how to deal with a special case where there's a lower randomized M reduction, a reduction making just one query, and if the query answers yes, then the answer is yes, otherwise the answer is no, from L to K of n minus omega log n. And the idea is, well, I mean, how are you going to exploit a reduction to the Congo random strings? Congo random strings are uncomputable. Somehow you're going to look at what the reduction does and show the reduction itself needs to know something about the Congo complexity strings that it outputs. So the idea is to distinguish between yes and no instances for L simply by looking at properties of distribution sampled by this reduction. So randomized reduction. So in some input when you fix an input x, it leads to a distribution d of f comma x. And it turns out that the entropy of this distribution sort of allows you to classify instances as yes or no instances. Suppose that D has high entropy, then we're able to argue that with noticeable probability, 1 over n to the omega 1 probability, D of f comma x outputs a string of high Congo complexity. While if D has low entropy, then with noticeable probability again, we can compress the output of the distribution, and hence the output has low Congo complexity. And because we assume that reduction is very, very low error, figuring out whether D has high entropy or not is enough for us to divide instances into yes and no instances. To solve it, we just need to distinguish between high and low entropy with a sampler D of fx, and that's a sampler as described by polynomial size circuits, and such a problem is known to be in statistical zero knowledge, and that's an AM, it's a co-AM. So that's sort of a rough argument for a very special case when you have a low error randomized M reduction. And it's sort of it's close to our eventual argument, which is more complex. What we really do for randomized polytime non-adaptive reductions is to try to simulate L and AM and say co-AM in 2 steps. First, we try to replace this Kolmogorov random oracle with an approximate counting oracle that counts the number of pre-images of a string y according to this randomized reduction M. And then we aim to simulate the approximate counting oracle in AM and say co-AM using several standard protocols. So neither of these steps is that easy to implement. There's several technical difficulties. We need to use a non-standard notion of oracle. We need to use a perturbation argument, second step, and so on. So lots of difficulties, but this is a plan that we're on the whole able to carry out. So how about theorem 2? So let me remind you what theorem 2 is. Suppose there's a polynomially bounded t prime, such for large enough t as function of t prime. There's a nice, I'm not going to quantify what nice is, suppose it's stock, polynomial honesty, and some minor extra condition. A nice randomized time t prime non-adaptive reduction from SAT to k subscript t, gap version of it. Then either E is non-atomic circuits of size 2 little n or n equals co n. So what we're going to do is we're going to show that under the assumption that E requires exponential size non-atomic circuits, under this delamination assumption, we're going to show that we can actually simulate in some sense this k subscript t oracle by a k oracle. We can somehow the two oracles are going to look indistinguishable to this randomized time t prime reduction. So we can just replace this k subscript t oracle by a k oracle. And that will allow us to use theorem 1, because then we'll know that any language L that we're reducing to this will have to be an AM and say co-AM. And in fact, it's enough for us that the reduction works for tally languages in NP, because we then get that every tally language in NP is in AM and say co-AM. Under the delamination assumption we have here, we also get that every tally language is in NP and say co-NP, and then that implies that NE equals co-NE. So that's the general idea for proof of theorem 2. Let me just end with some open problems. Can we extend our results to give evidence against NP-Completeness to MCSE, our original goal under randomized polytype non-adaptive reductions? There are some kinds of evidence that exist, but only for very special kinds of reductions. Murray and Williams showed that MCSE is not NP-Hardnes randomized sublinear projections. So like every output bit is an input bit or its negation, and this is computable in sublinear time, so it's quite restricted. In joint work with Rahul, Lango, and Handel and Ren, I showed that under the assumption that one-wave function NC 0, under the standard crypto assumption, there are no randomized local reductions from SAT to multiplicatively approximating circuit size. And here, the multiplicative approximation is something that depends on the locality. So the locality is, say, n to the delta. If each output bit depends on n to the delta input bits, then the circuit size approximation would be like n to the 4 delta. So there's some sort of trade-off going on here. But these are both for quite weak kinds of reductions, and maybe you can say something much stronger kinds of reductions. And on the other side, it would be interesting to explore ways in which randomized adaptive reductions or non-uniform reductions could be useful in this context. These are known to be useful for other kinds of meta-complexity problems, which are complete for X plus P space, but we don't really know how to use such reductions and exploit the power of those such reductions for NP problems. That's all I have to say. Thank you.